Starlight is a layer 2 payment channel protocol for the Stellar network. I'm Leigh McCulloch. I'm a principal software engineer at the Stellar Development Foundation. I joined the engineering team in 2019, and I work on ecosystem standards, core advancement proposals, and experimental projects like Starlight.
Hi, I'm Alec Charbonneau. I've been with SDF for about a year and a half, and I'm part of the product engineering team. I've worked on a couple different SDF products, such as the lab, Vibrant, and some data projects. So for the agenda today, first we'll explain why layer 2 tech like Starlight is relevant to Stellar. Next, we'll explain what are payment channels in general. And lastly, we'll give a demo of our Starlight payment channel and explain how it works as we're using it. Along the way, we'll see how two new proposals, CAP 21 and CAP 40, make Starlight possible, simple, and efficient.
So why layer 2? We've been experimenting with layer 2 to see if there are capabilities we could bring to Stellar users, specifically Stellar users who need to process large numbers of payments. Processing a large number of payments has an upper limit on layer 1 networks that guarantee consensus and provide fast transaction confirmations like Stellar. The Stellar network today is configured with an artificial limit of 1,000 operations per ledger. This limit is controlled by the network, and it's something that validators on the network can vote on. What this limit does is prevent more transactions from being distributed when the limit is reached. It does this even if the network is capable of processing more, and the network sets this limit to promote financial inclusion and promote decentralization. It ensures that the community running the network, the people who are running validators or hosting archives, are able to do so with predictable costs, affordable, and readily available hardware. So this widens the funnel for who can run the network. And this is really important to us because Stellar is a borderless and open network. And our mission at SDF is to use the Stellar network to create equitable access to financial services. So ledgers on Stellar occur every 5 to 10 seconds. And if we spread that 1,000 operations over 5 seconds, we get approximately 200 transactions per second. We've been exploring the use cases of Stellar users who have high throughput requirements. And by high throughput, I mean volumes that exceed these limits by many orders of magnitude. We've been exploring how these users can secure their payments on the Stellar network without performing each individual payment on the Stellar network. We've been considering many different use cases, but we've focused on users who need to move large volumes of payments directly with another user. That's why we've been experimenting with payment channels.
So what are payment channels in general? Payment channels are a layer 2 technology that enables fast and instantaneous payments between two parties. The payments occur off network, but don't require either participant to trust each other. Payment channels can do this because of the cryptography and the security of the underlying blockchain. So to open a channel, participants first make an on-chain deposit into a channel. And then within the channel, participants can send each other payments. These payments are done off-chain, so the frequency at which the participants can send to one another is much higher than if they were using the layer 1 network alone. For each payment, the participants are forming a new agreement that gives a new final balance each participant will receive when the channel closes. When the participants want to close the channel, all the payments that happen between them are rolled into a final net settlement amount that then gets submitted to the blockchain. Leigh and I are now going to demo a prototype of a Starlight payment channel. For the demo, we have a private Stellar network running that includes prototype implementations of CAP 21 and CAP 40. These are two new proposals for the Stellar network. These are core advancement proposals currently in development, and they add new capabilities that we'll discuss as we encounter them. In this demo, we're going to open a channel, send some payments back and forth, and then close it. While we're doing that, we'll explain in detail how Starlight payment channels work.
So Alec and I both have a copy of the demo console application running locally. Our applications are connected to each other over a TCP connection and will communicate using some simple binary messages. On the left, you can see my console where I'll be entering instructions into the application. Alec is running the same application and he'll also be able to enter instructions. On the right, we have the dashboard that will display the state of the channel on the Stellar network, as well as the state of the channel off network. The graph at the top of the network, of the dashboard shows transactions that happen on layer 1 on the Stellar network. It'll be relatively quiet because we're running this demo using a private test network that's running here on my computer in a Docker container. And a note about that, if you'd like to replicate this demo, it's as simple as running the Stellar network in Docker and running our console application. And we'll have a link at the end of the talk to all of the code that's here. The first thing that we can see is on the right, there are two charts, one for each Stellar account that will hold assets for the payment channel.
So let's pause for a second and talk about why we're looking at charts of two Stellar accounts. The process of opening a Starlight payment channel begins with two Stellar accounts on layer 1. Each participant, me and Leigh in the channel, creates and starts out fully controlling an account. These accounts hold the funds of the channel, which will then be redistributed during the close. So the blue and orange charts show us the signers for the two Stellar accounts. So Leigh's on the left in blue and I'm on the right in orange. We can see that both accounts have a single signer. I'm the sole signer of my account on the right, and Leigh's the sole signer of his account, the local one. Now let's open the channel and see what changes.
Okay, I'm running the command to open the channel.
Cool. So we can see at the chart at the very top of the dashboard shows that the open transaction has been confirmed in a ledger on our private network. Below it, we see the signers for the two accounts changed. The accounts are now both multi-sig accounts, as both accounts have two signers, me and Leigh. Leigh and I are now joint signers for each account. That means that we both must sign transactions for these accounts going forward. So let's go over how this open process works. When Leigh opened the channel, his application generated 3 transactions. These 3 transactions form our open agreement. Leigh and I both sign each transaction to make the agreement valid. During this process, we both share our signatures in a single message so that either of us can attach all the signatures to the transactions and submit it to the network. When I received Leigh's signatures, my application first validated the agreement, then signed the transactions, and then sent my signatures back to Leigh. And at this point, we've both just signed the open agreement. Now, I said 3 transactions, and these 3 transactions I've been referring to are the open, the declaration, and the close transaction. The open transaction does what you think it would by its name. It opens the channel. And it accomplishes this by changing both Stellar accounts into multi-sig accounts, which we saw on those 2 charts. The declaration and close transaction together form a close agreement, which can be used to close the channel. We'll explain how close agreements work when we do a payment in a second. The last step in the open process is submitting that open transaction to the network, which is what Leigh did in the demo. By submitting that open transaction to the network, Leigh effectively opened the channel. So that's how the open works. But looking back at the dashboard, we can see that neither account has a balance once we look at the balances charts. So Leigh will be depositing $10,000 of a US dollar asset into the accounts on this private network.
Yeah, so this is a test network. So this isn't real US dollar assets we're using, but it's an issued asset like any other asset that you can issue or hold on the Stellar network.
Cool. The deposits are in. So we can see on the left pie chart that the account balances on the Stellar network have updated, showing our contributions on our private network. The right pie chart shows our balances of the channel off network. To briefly talk about deposits, Starlight channels allow both participants to make deposits to the channel at any time without involving the other participant. And they do this with a regular payment to their respective accounts. There's no new agreements that need signing, and the existing agreements still stand. Any amount that I deposit will automatically belong to me when the channel closes, and any amount Leigh deposits will automatically belong to him. So it's really easy for me or anyone really to top up an existing channel. And I can use a Stellar Anchor, an exchange, or a wallet to send funds, which makes Starlight channels as simple as a regular Stellar account to integrate with existing payment rails. Okay, so now let's do a payment using our created Starlight channel. I'm going to send Leigh $4,000 of this US dollar asset that was deposited. So on my application, I am paying Leigh $4,000.
Okay, so we can see on the dashboard that the payment immediately changed the balance of the channel. The payment channel operates as a net settlement mechanism. So when Alec paid me $4,000, we updated the channel to pay me $4,000 when it closes. I'll pay Alec $6,000 of the US dollar asset. Let's watch the dashboard and see what happens. So we see the balance immediately swung back the other way. If we were to close the channel now, I would pay Alec $2,000 to settle the account. And the dashboard confirms this. The orange area of the graph has gotten larger because Alec owns more of the final balance of the channel. He owns the $10,000 that he contributed, plus the $2,000 that I owe him after the two payments. Let's have a look at what's happened in the background when we made the payment. So when Alec paid me $4,000, he proposed a new close agreement that superseded the agreement that we signed when opening the channel. When I received the new agreement, I checked that it increased my balance and then signed and returned my signatures back to Alec.
And we're exchanging the signatures for these transactions with a single message, which can be unsafe to do in some multi-transaction protocols. But we'll come back to this soon and explain why it is safe to do with Starlight.
So when we sign a close agreement, we're signing two transactions, the declaration and the close. These transactions go in pairs. Together, they're used to close the channel. They contain what we're agreeing will be the final state of the channel. But these transactions won't be submitted to the network. That's because every time we send a payment on the channel, we agree to a new pair of transactions. And those new pair of transactions, they supersede the previous. So let's get an understanding of what these transactions do, starting with the declaration. The declaration is responsible for announcing on-chain that the close process is beginning. It does that by placing the channel in a state where the close transaction is allowed to execute. And not just any close transaction, but specifically the close that was paired with the declaration. It does this by using a very simple feature that exists on the Stellar network today, as well as an extension to that feature that we're proposing in CAP 21. That feature is sequence numbers. An account's transactions have sequence numbers that provide an order to how those transactions must be executed on the network. They're a simple number stored in the transaction that must increase by 1 for every transaction. For example, if we've created a series of 4 transactions, 1, 2, 3, 4, the transactions must execute in that order. 1 must execute before 2, 2 must execute before 3, and so on. That's how sequence numbers behave on the Stellar network today. Now we're proposing an extension to their capabilities in CAP 21. And what CAP 21 allows us to do is to say that a transaction such as transaction 4 is valid as long as transaction 1 has executed. we no longer need every transaction between 1 and 4 to execute. Transactions 2 and 3 can execute, but they don't have to. And if they are going to execute, they have to do it before transaction 4, because once transaction 4 is confirmed, 2 and 3 are no longer valid. Using our transactions so far as an example, Alec and I signed 3 transactions at the beginning: the open, the declaration, and the close. The first payment that Alec sent me created a new close agreement that occupied sequence numbers 4 and 5. If we decided to close the channel after that payment, we would simply submit transaction 4, declaring the start of the close process. Submitting transaction 4 puts the channel into a state where the next transaction, transaction 5, the close transaction, can execute. This capability to skip ahead to a more recent declaration is also how a close can be disputed. So if in our scenario, Alec had regretted the payment that's captured in transactions 4 and 5, he might try to start the process, the close process, with transaction 2. And if I saw that happen, I could dispute the close by submitting transaction 4. Remember that once transaction 4 is submitted, lower number transactions can't execute anymore. So this prevents the close from completing with transaction 3, which contains that old state.
Because we can always dispute an old transaction with the latest transaction, there's no need for us to keep old transactions, and we can delete them. Participants in a Starlight channel only need to store a tiny amount of data to maintain the safety of the channel, even if the channel is long-lived and even if they do millions of payments. This makes Starlight channels very easy to scale. They don't add a data storage burden to your infrastructure. Let's take a look at the second transaction in the close agreement. And that second transaction is the close transaction. The close transaction is responsible for finalizing the close of the channel. To do this, it contains a few operations. The first is a payment operation. This payment operation is a net settlement that I referred to earlier, resulting from all the payments that occurred in the channel up to that point in time. So far in our demo, we've sent 2 payments. I paid Leigh $4,000 and then Leigh paid me $6,000. If we close the channel now, the net settlement would be $2,000 owed to me from Leigh. In addition to the payment, the transaction also contains 2 operations that modify the signers of Leigh and my Stellar accounts. Those operations give Leigh and I full control of our accounts again, like it was before we opened. So together, these 3 operations close the channel. There's one more attribute of the closed transaction that's really important. And that attribute is a relative time lock. Relative time locks are a new capability that Cap21 brings to the Stellar network. Normally, transactions from the same account can execute immediately, one after another. But with a relative time lock, it introduces a delay that must occur between 2 transactions. With Cap21, we configure the close transaction so that there must be a delay between itself and the declaration. So if I submit a declaration, like in the example that Leigh gave, this delay is what gives Leigh that time to dispute the closing of the channel.
So that's how the declaration and the close transactions come together to close the channel. We mentioned earlier that one of the challenges with protocols that require participants to sign multiple transactions is that it can be unsafe to share signatures for both transactions in a single message. But as we saw, participants in the Starlight channels do share all messages at the same time. The reason we do that is for efficiency. By eliminating network messages, we maximize the number of transactions we can perform in a second. Solving this problem is where a new capability proposed in Cap 40 comes in. That capability is atomic signature disclosure. So let's walk through an example to understand why this problem exists and how atomic signature disclosure solves it. Let's assume that Alec signs 2 transactions assuming that if one executes, the other must then be valid, and say that I sign and submit to the network only one of those transactions. Alec would have no way of submitting the second transaction because he doesn't have all of the signatures for it. Cat40 addresses this challenge by introducing a new type of signer to the Stellar network. That signer is the signature of another transaction. Atomic signature disclosure then uses CAP21 to embed that new signer and its signature inside the first transaction. Starlight channels use CAP40 and CAP21 to require participants to disclose the signatures of the close within the declaration. This means that the first transaction is not valid unless the signature for the second is also disclosed. So if we rerun that same scenario using the process that's defined in CAP40, if I was to completely authorize the declaration and submit the transaction to the network without sharing the close signature with Alec, Alec would see the transaction on the network and be able to copy that embedded signature and attach it to the close. That would allow Alec to submit the closed transaction. And so atomic signature disclosure makes it safe to share signatures in a single message. Because it requires the disclosure of all the signatures before any transaction is valid. So you will have noticed that we've mentioned CAP21 a few times so far, and that's because the proposal is full of new features that add new capabilities to the Stellar network. One that I want to touch on because it's relevant to payment channels is the ability to add hash signers directly to transactions as a precondition. This will give us the ability to create the hash component of a HTLC in a stateless way. The hash will live only within a transaction off network. We think this will be useful for anyone who implements multi-hop trustless payment channels in the future. So let's jump back to our demo. So we did some one-off payments and we're able to see what effect they had on the balance. Let's generate a large number of payments. I'm going to generate 1,000 payments. They'll be sent to Alec one at a time. Each payment will wait for the previous payment to complete before sending. Because we're doing these payments serially, the speed at which we do the payments will be limited by our network latency. The reason for this is that each payment is a message that must travel from me to Alec and from Alec back to me. Looking at the bottom, I've got a ping going between our computers so we can see what our latency is. It looks like we're under 30 milliseconds. We're actually, it's moving around a little bit, but between 20 and 30. So we can expect to see at least 33 transactions per second. Okay, send these. So we can see looking on the dashboard, watching the dashboard on the right, we're getting 38 transactions per second. So not all use cases require that the result of every payment be confirmed before another payment begins. In Starlight channels, we've been experimenting with buffering payments. Buffering is the process where we collect payments where we wait for the opportunity to propose the next agreement. While we're waiting the 30 milliseconds for our agreement to be authorized, we collect the payments into a buffer. And once the agreement is authorized, we can immediately propose the next agreement. That next agreement will contain all of the payments that have been buffered during that 30 millisecond wait. We send the details of each individual payment, but we deliver the buffer in a single agreement. A payment channel is fast, so we can deliver many buffers per second. We're just limited by how much bandwidth we have to transmit the buffer over the network. So I'm going to send Alec a larger number of payments now. I'm going to send him 100,000 payments. I'm setting our maximum buffer size to 10,000. That means that our payment channel is going to propose a new agreement as soon as it can, but while it's waiting for the opportunity, it'll allow up to 10,000 payments to collect in the buffer. It'll then send those payments, 10,000 payments at the next opportunity it gets. Okay, so 100,000 payments and 10,000, maximum 10,000 buffer. Okay, so it's already finished. We can see we got around 220,000 transactions per second equivalent in the time period we sent it. So we delivered all those payments in less than half a second. We're able to do this because we're using the bandwidth we have available to us, along with the fast finality of the payment channel, to send all those payments over the wire. So let's try another. I'm going to send Alec 10 million payments, but with larger buffer sizes this time, up to 95,000 payments in a single buffer. This might seem a little bit unreasonable, but at this size, our buffers are small when compressed. We should see the buffers be around a couple hundred kilobytes. So as long as we have the bandwidth to move a couple hundred kilobytes quickly, we're still going to get fast finality. Okay, so 10 million payments in buffers up to 95,000. Okay, so it's getting up to around 1.2 million transactions per second or payments per second. So that's great. That's a lot larger. You might be wondering how buffering over payment channels like Starlight is different to batching payments, which is a really common pattern in slow traditional payment systems. And the answer really is that payment channels aren't slow, they're fast. This difference means that buffering payments doesn't compromise on time to finality or time to confirmation. The payment sender still gets a fast confirmation in milliseconds, but instead of getting fast confirmation of one payment, I'm getting fast confirmation of an agreement that's made up of many payments that occurred over the last few milliseconds. This is really a similar principle to blocks in blockchains. So let's move on to closing the channel. Closing the channel means submitting the declaration, waiting the delay period, and then submitting the close. But when we're both in agreement about closing the channel, waiting the delay time between the declaration and the close is unnecessary.
Cool. When Leigh kicks off the close process, his application will modify the last agreement that we agreed to, removing the delay, then re-sign the transactions and send those signatures to me. Then my application will verify those signatures, make sure it's the same balance as the last agreement we agreed to, and if so, sign it, and then send my signatures back to Leigh. At this point, the close agreement, which has both Leigh and my signatures, can be submitted to the network. So let's go back to the demo, and then we'll close our channel.
Okay, so I'm going to run the close channel, the close command. Also going to expand these account signers so we can see the state of our account. Okay. I'm running the command. So on the right, we can see the balance of the two Stellar accounts. These should update. Okay, so our signers have updated. There we go. And the balance is updated. Great. So yeah, we can see that the balance of the network now matches what the balance of the channel was. And we can also see the signers. So at the top, both of our Alec and I, both of our Stellar accounts, we have full control over again. So we're no longer jointly controlling them. So fantastic. The payment channel worked. So we opened the channel. We performed millions of payments really quickly. And we're able to close the channel quickly as well. And we were able to do that efficiently. We only needed to store the most recent agreement without needing to revoke previous agreements. Because of CAP 21, we were able to communicate efficiently with a single message in either direction. And because of CAP 40, atomic signature disclosure, we were able to communicate it efficiently with a single message because of CAP 40. And we also saw that we were able to recover in some situations, like where we're able to dispute fraudulent behavior using CAP21 and able to recover signatures that weren't shared using CAP40.
Sweet. So what's next for Starlight and payment channels at Stellar? So right now we have a public repo on GitHub at the link on the slide that hosts Starlight for anyone to look at. And in that repo, you'll find our CAP21 and CAP40 proposals, as well as a Docker image for running your own private network with these proposals implemented, which is what we use during our demo today. And our prototype SDK is also there, which is written in Go. And there's some example code using this SDK, both with and without buffering. In terms of what's next, we have ideas for how we can improve and build upon what we've already designed. And we're actively pursuing getting CAP21 and CAP40 accepted into an upcoming protocol release. If payment channels on Stellar interest you at all, we invite you to get involved. You can talk to us on our GitHub repos discussion board about anything related to Starlight. And please feel free to experiment with our prototype SDK yourself. Thank you.
Thank you.